Okay. So you take a small enough triangle such that it's in a convex neighborhood. So you have a unique geodesic connecting to 2 points. And the signed distance is now the positive length of this distance if the points are space-like related. So if the geodesic connecting them is space-like, it's negative length if they are time-like related, and it's 0 if they are null related. So this kind of signed distance is not a distance in the sense of a metric space, but still they were able to characterize the sectional curvature bounds with respect to this signed distance. Okay, so what to do in the Lorentzian case, because this only works for smooth Riemannian, semi-Riemannian manifolds, because you need convex neighborhoods to define the signed distance. So every Riemannian manifold is canonically a metric space. So what is the analog for Lorentzian manifolds or spacetimes? As we heard, spacetimes are time-oriented Lorentzian manifolds. And our suggestion, what is the analog of a metric space in the Lorentzian setting? It was worked with Mike Kunzinger, so-called Lorentzian pre-length spaces, and Lorentzian length spaces as analog of metric length spaces. Just give you the definition. So by now there are several axiomatizations and also names. For example, you could call it also metric spacetimes if you want. So a Lorentzian pre-length space is a metrizable topological space. You have two relations on it. Less or equal is a pre-order, so it's reflexive and transitive, and less a transitive relation contained in less or equal, and tau a lower semi-continuous function. And then this is called a Lorentzian pre-length space if the tau satisfies the reverse triangle inequality for all triples of points which are causally related like this. And it's compatible with the relations as follows, that it's 0 if they are not causally related, and it's positive if and only if they are time-like related. And tau is called the time separation function. So you could put everything into tau, for example, by allowing the value minus infinity and saying that they are causally related if and only if the value is non-negative. But we opted for this, this choice because actually in spacetimes of low regularity, you have a time separation, you have these causal relations, and this is kind of a compatibility condition. And in smooth spacetimes, this is always satisfied. So this is the first example. You have a smooth spacetime with the usual time separation function, given as the supremum of the G-lengths of all future-directed causal curves from P to Q, or 0 if there is no future-directed causal curve connecting them. But you can also look finite-directed graphs as Lorentzian pre-length spaces by taking the maximum number of steps you need to get from one vertex to the other. And this is, for example, in the causal set approach to quantum gravity. But for example, also spacetimes of low regularity and Lorentz-Finsler spaces are fall into this framework. So if you have a Lorentzian pre-length space, now you can talk about causal curves as follows. They are totally ordered by less or equal, and similar, a time-like curve is totally ordered by less. Analogously, you can define null curves as saying that they are totally ordered by less or equal, but no 2 points are time-like related. And you see immediately that this is that does not give you the same thing as in the space-time case in general. So if you take the Lorentz cylinder, which is just take a strip in Minkowski space-time, and you identify, then what happens is that you get closed causal curves. So this would be the local light cone. But if you go here, then you come back here. And from here, you can go again 45 degrees. So actually, every pair of points is causally related. So every curve is time-like and causal. So this tells you that you need some causality conditions. Then another illustrative example is this curve in Minkowski spacetime, in three-dimensional Minkowski spacetime. So this is like, you have the light cone here, and this curve like spirals on the boundary of this light cone. And this has a null tangent with respect to the Minkowski metric, but it's actually time-like in this relation sense, because it's not a null geodesic, it's not null pre-geodesic, but any 2 points in the curve can actually be connected by a straight time-like curve. So you see that for causal curves, you need causality conditions, and for time-like curves, it might be different, but the length agrees. And first, we showed that if you have a continuous, strongly causal spacetime, then actually the different notions of causal curves agree. So strong causality means that there are no almost closed causal curves. So not only are there no closed causal curves, but there is no sequence of curves where the endpoints converge to each other. Yes. Yeah. Exactly. Yeah. So it even holds for spacetimes of low regularity. Then, once you have defined what causal curves are, you can define the length with respect to tau, similar to length of curves in metric spaces. Just you have to take the infimum over all the time separations of points on the curves. Then this is really a good notion of length. It's additive and invariant under reparameterizations. And then this curve we just had, then this is time-like, but actually has tau length 0. And as I said, this has actually a tangent which is null in respect to the Minkowski metric. So you see that actually the length is preserved, these two notions. And this holds in general for smooth, strongly causal spacetimes. Then this length is actually the length you get via the metric. And the funny thing is that actually Penrose defines the length like that in his one booklet on Lorentzian geometry, and he never ever bothers to show that this is the same length as you would get by just integrating the norm of the tangent. Then once you have this, you can define maximal causal curves as analog of geodesics. These are just causal curves which realize the time separation between the endpoints. And then we get to Lorentzian length spaces. You need some additional assumptions, which I will not talk about here for time reasons. But basically, it means that the time separation is intrinsic. So the time separation is actually, so the time separation you start out with is actually the supremum of the length of the curves connecting the 2 points. So the future directed causal curves from X to Y. And then you can also define what is a regular Lorentzian length space, is that if causal maximizers are either time-like or null. Because in spacetimes of low regularity, you have examples where the maximal causal curves have segments which are null and time-like. And for example, in Lipschitz spacetimes, this cannot happen, but there are Hölder spacetimes where this can happen. So this is kind of a synthetic notion of regularity. And then this example we already had, a smooth and strongly causal spacetime is a regular Lorentzian length space because the length actually agrees. But also, you can look at continuous and strongly causal spacetime if you assume that they are causally well behaved, which is called causally plane, which means that there are no causal bubbles. Then this is a Lorentzian length space. But actually, there was recently work by Ling who shows that actually just continuous and strongly causal is enough if you change slightly the definition of time-like curves. You can still view the continuous strongly causal spacetimes as Lorentzian length spaces. Okay, so now this is the basic setup. Now let's talk about curvature, and in particular first triangle comparison. So these are the model spaces of constant curvature k in the Lorentzian case. So for k equals 0, this is just two-dimensional Minkowski spacetime. For k positive, this is the simply connected covering manifold of the zeta space, which is here, for k equal 1. And for k negative, this is the simply connected covering manifold of scaled anti-de Sitter space. And then Harris and Alexander Bishop, they showed that if you have time-like triangles, so 3 points which are time-like related, and the side length is small enough, depending on k, then there's a unique, up to an isometry of this model space comparison triangle in this model spaces. So you can do triangle comparison. And that's what we did. So we say that the Lorentzian pre-length space has time-like curvature bounded below if every point has a neighborhood U such that tau, so the time separation on this neighborhood, is finite and continuous. Any 2 points which are time-like related can be connected by a maximal causal curve in U from X to Y. And then the actual triangle comparison is that if you take a small enough time-like geodesic triangle, so the 3 points X, Y, Z, which are in this neighborhood, such that there is a comparison triangle, so the side lengths are not too large in the model space MK. Then you take 2 points P and Q, and take 2 points P bar and Q bar in the comparison triangle, which have the same time separation from the endpoints. Then, if the time separation of PQ is bounded above by the time separation in the model space, then it has curvature bounded below. So you'd really flip. So if for curvature bound below, the time separation is bounded above. And similar for time-like curvature bounded above, you have the other inequality. And then recently, colleagues here in Vienna, Beran, Kunzinger, Ohanian, Roth, showed that if you have a smooth Lorentzian manifold, where you have time-like sectional curvature bounds, so just bounds on the time-like sectional curvature, not this Alexander Bishop bound, where you also have the space-like sectional curvatures, then this fulfills is equivalent to this triangle comparison. And also, time-like curvature bounded below implies that your maximal time-like curves do not branch, which is analogous to the Alexandrov case, where in spaces with curvature bounded below in the triangle comparison sense implies that the minimizers, the geodesics, do not branch. Okay, then let me mention some selected applications. So our first application was actually to this question I mentioned in the beginning of inextendability of spacetimes and the cosmic censorship hypothesis. It was joint work with Mike Kunzinger and James Grant. We showed that actually you can show that spacetimes are either inextendable as regular Lorentzian length spaces, or you have a blow-up of curvature. And this was something which was not possible before because you couldn't talk about curvature in the extension. So we looked at a lot of examples, which we called generalized cones. This was joint work with Stephanie Alexander, Melanie Graf, and Mike Kunzinger, and I will talk about this in more detail. Then also Andrea mentioned already that Robert McCann and Andrea and Stefan Suhr, they characterized time-like Ricci curvature bounds on smooth Lorentzian manifolds with tools from optimal transport. And then Andrea and Fabio Cavalletta used the setting of Lorentzian pre-length spaces to give a synthetic notion of time-like Ricci curvature bounded below. Also, Andrea and Stefan Suhr, they gave a synthetic notion of vacuum Einstein equations by saying that, okay, it has time-like Ricci curvature bounded below by 0, and it has time-like Ricci curvature bounded above by 0 by giving the appropriate definition of time-like Ricci curvature bounded above. And for example, time functions were studied by Burcher and Garcia-Hevelink. Also, we studied an analog of Hausdorff measures on these Lorentzian pre-length spaces and a kind of dimension for these spaces. It was joint work with Robert McCann. And one advantage of leaving the framework of smooth manifolds is that gluing becomes more easy. This was done by Beran, Roth, and Roth. We studied hyperbolic angles and angle comparison as an equivalent definition of time-like curvature bounds. This was joint work with Tobias Behrendt and independently was done by Barrera, Montes de Oca, and Solis. Then a big application was the splitting theorem for globally hyperbolic Lorentzian length spaces, which have time-like non-negative Ricci in the triangle comparison sense. This was done by Beran, Ohanian, Roth, and Solis. And another advantage of leaving the framework of smooth manifolds is that causal boundaries are also now Lorentzian pre-length spaces, and this was always an issue in general relativity, that causal boundaries are not manifolds anymore, and somehow they have to be treated separately, but now they fit into the same framework. And also last year, quite surprisingly, there was a paper by Law and Lucas which used our framework for machine learning. So apparently there is some demand in machine learning to embed directed graphs into spacetimes, and this was done for particular spacetimes like Minkowski, de Sitter, anti-de Sitter. And Law and Lucas realized that actually the only thing they know that they need is the time separation function and the causal relations, and then they can describe the algorithm in full generality, and then only in the implementation they choose some specific spacetime. So that was quite surprising. Okay, and so first application, or I want to go more into detail with this called generalized cones, and then talk about work in progress. So this was joint work with Stefan Alexander, Melanie Graf, and Mike Kunzinger. So we call it generalized cone. Do not confuse it with warp products in the metric case, but yeah, okay, it's still a bit not so, yeah. So its generalized cone is you take a metric space, an open interval, and a function which is non-negative, continuous function negative, and you take the product. And you should think of it as a word product with one-dimensional base, where the base is now has like is not Lorentzian or has a minus. So if you take a curve gamma, which has the components alpha, beta, so alpha goes into I and beta into X, absolutely continuous, then alpha dot exists almost everywhere, and the metric derivative of beta exists almost everywhere. So the metric derivative is given here and satisfies that if you integrate it, you get the length of beta. Then you can give a Lorentzian structure on this generalized cone as follows. So you take a curve which is absolutely continuous, then you say the curve is time-like if minus alpha dot squared plus f squared and times the metric derivative squared is negative almost everywhere. It's null if this is 0 almost everywhere, and non-negative causal if it's non-negative, non-positive. And it's future directed if alpha dot is positive, and past directed if alpha dot is negative almost everywhere. And the length of a causal curve is just minus this integrated and the square root. And for this talk, let's assume that X is now a locally compact geodesic length space. Then you can actually describe the causal structure of these generalized cones in quite detail. In particular, the causal relations and the futures and pasts are defined as usual. We're just saying, okay, 2 points are time-like related if there is a future-directed time-like curve connecting them. And the time separation is defined via this length we just had. So the time separation is the sup of the length of future-directed causal curves from X to Y, or 0 if there is no such curve. And then you have fiber independence. So if gamma is a future-directed causal maximizer, which components alpha beta, then the fiber component beta is minimizing in X. And of course, the converse does not hold because you have to choose the right parameterization for alpha. But the fiber independence tells you that the base component alpha depends only on the length of beta. It actually doesn't depend on the metric space. So if you take another metric space and another minimizing curve, which has the same length, the same speed, then this new curve where you just replace beta with beta prime is maximizing causal time-like in this generalized cone where you place X with X prime. And so in particular, the time separation of P and Q depends only on the base component of P, the base component on Q, and the distance in the fiber. And of course, on the warping function. And this allows you to simplify a lot of things. So then the question is the future of a point or the time-like relation open, and does push-up hold? So push-up is saying that if you have a time-like curve and then a null curve, do you have a time-like curve connecting the endpoints, which holds in every smooth spacetime but fails for spacetimes of low regularity? And actually, yes, this is true here, because you can actually write, so I think for time reasons I will skip the details, but basically you can write the future of a point quite explicitly via this ODE here. So in particular, it's open and push-up holds, and this was actually also a new result for continuous Lorentzian manifolds, where you take a continuous Riemannian manifold and a continuous warping function. And also the boundary is a continuous graph over the ball in the fiber. And J plus is really the time-like relation and the boundary. So the causality is really as good as you want. In particular, it's a Lorentzian pre-length space, and a little bit more work you can show that it's a strongly causal Lorentzian length space, which is regular. So the maximizers are either time-like or null. Then in this setting, we were able to show first synthetic singularity theorem. So here, a singularity again is like an incomplete causal geodesic. So, and that would mean that f, the warping function, has to go to 0 in finite time. So if you have a generalized cone y, where the interval is AB, and it has time-like curvature bounded below by k in the triangle comparison sense, then f is actually k concave. Similar, if it's time-like curvature bounded above, then it's k convex. And if k is negative, then actually A is finite and B is finite. Hence, the time separation function is bounded by B minus A. so it's time-like geodesically incomplete to the future and to the past. If k is 0 and f non-constant, then you have two cases. So either A is finite or B is finite. So either it's past time-like geodesically incomplete, which would correspond to the Big Bang scenario, or it's future time-like geodesically incomplete, which correspond to the Big Crunch scenario, where everything goes to comes together in one big in one point. And for example, to see when does the time-like the cone have time-like curvature bounded below. So if you take k prime and you take a function which is a k prime concave, and the metric space has curvature bounded below in the Alexandrov sense, where k is now the sup over k prime times f squared minus f prime squared, then the generalized cone has time-like curvature bounded below. So this is like a sufficient condition to ensure that the time-like cone has a curvature, the generalized cone has time-like curvature bounded below. And then we want to study, so this was paper some time ago, and now we want to study what happens with time-like rigid curvature bounds in these cones. And for that, we have to introduce, we not only need the Lorentzian space, but we need a measure. Andrea mentioned that, but I will give a bit more details. So this is following the work of Andrea and Stefan Suhr and Robert McCann in the smooth spacetime case. Then Andrea and Fabio Cavaletti gave the following definition. But for first, we need some notions, like the Lorentzian-Wasserstein distance. So you take P now is in 0, 1, and you integrate the time separation to the power P over all couplings of mu and nu, which are causal, so which give full measure to the causal relation. So you can think of that you have two probability measures. They have their support, and the support is such that the product of the support is contained in the time-like relation. So because the transport now in the Lorentzian case happens along maximal causal curves. So it could also be that there is no such coupling, and then this would be minus infinity. Where in the usual optimal transport, there is always a coupling, like the product measure. This is not the case here. Then we call two probability measures time-like p-dualizable if there exists an optimal coupling, which actually gives full measure to the time-like relation. Then we can study the Boltzmann-Shannon entropy as in the metric case. So we have some reference measure m on the Lorentzian preline space and integrate rho log rho if mu is absolutely continuous with respect to m, and this is integrable, otherwise just set it to plus infinity. Then the definition of a TCD space or TCD-Kn space, so it means that it has time-like rigid curvature bounded below by k and dimension bounded above by n, if for all couples of probability measures, which are absolutely continuous and time-like p-dualizable, there exists a time-like LP geodesic. So a geodesic with respect to this Lorentzian-Wasserstein distance, so meaning it maximizes the distance between points on this curve, such that the entropy is semi-convex and satisfies this inequality in the distributional sense, where pi is now an optimal coupling which gives a full measure to the time-like relation. Then you can define also the time-like measure contraction property if this holds where mu1 is just a delta at x, where x is in the future of the support of mu0. Okay, and then this is joint work with Matteo Callisti and Christian Ketterer. If you have an essentially non-branching CD space, which has the curvature bound below by eta times n minus 1 and dimension bound above by n, and f is kappa concave in the distributional sense, then the generalized cone with this measure, f to the power n, the r times the reference measure of x, then this satisfies the time-like measure contraction property, kappa times n, and of course the dimension is 1 larger. And also in the converse direction, we have a result that if you have a generalized cone with this reference measure, and this satisfies the time like a CD condition with kappa n and dimension bound above by n plus 1, then X is a CD space where the Ricci curvature is bounded below by eta times n minus 1, and F is kappa concave, where eta satisfies this condition here. So we can relate the curvature of the base to the curvature of the generalized cone and vice versa, similar to what we did for triangle comparison. We'll have some time. So then this is another work in progress with Tobias Beran, Matthias Braun, Matteo Callisti, Nicola, Robert McCann, Agam Ohanian, and Felix Roth. And Nicola actually mentioned that yesterday, but we give a bit more details. So in a smooth spacetime, if you take a function which has time-like gradient and a time-like curve gamma, then by reverse Cauchy-Schwarz, you can integrate the difference of f at the endpoints and bound this from below by the reverse Cauchy-Schwarz inequality by the norm of the gradient times the norm of gamma dot. And if we want to make sense of that in the synthetic sense, in the synthetic setting, we only need to know what the norm of the gradient is and what is the norm of the tangent of gamma. We don't need to know what the gradient is, and we don't need to know what the tangent of gamma is. And in the metric case, this was quite successful, and it's called the minimal weak upper gradient and metric speed. And we want to develop something like that in the synthetic Lorentzian case. But we decided to not call it a maximal weak lower gradient because it's not really a gradient. So we call it a maximal weak subslope. But first we need causal speed. And for that we differentiate the reverse triangle inequality. So take t, which goes from the half square, s less equal t, into 0 infinity, such that it satisfies the reverse triangle inequality. So TRS plus TST is bounded above by TRT, where R is less equal S is less equal T. Then there exists a maximum measure mu among Borel measures nu on the unit interval, such that the measure of an interval AB is bounded above by T at A and B. Then using that, we can apply this to causal paths. So they need not be continuous, and this will be important. You set TST as the time separation of gamma S and gamma T. Then this satisfies the reverse triangle inequality because the tau satisfies the reverse triangle inequality and gamma is causal. Then there exists a maximum measure, a mu, which we call the causal speed of gamma. And we have this Lebesgue decomposition, where this is the absolutely continuous part and this is the singular part. And important thing is that gamma need not be continuous. And we want to develop a calculus for time functions, because so the first part was to get an analog of this here. This is the causal speed. We did that. So now let's focus on this part here. The time function in that setting is just a function which is monotone with respect to the causal relation. So it's if x is less or equal y in x, then f of x is less or equal f of y in R, or the extended real line. We have to take, so M is again a reference Radan measure, and a probability measure on causal paths is a test plan if it has bounded compression. Then we can define what is a maximal weak subslope. So F is a Borel time function, G is a weak subslope. If for every test plan pi, you can bound this difference here, integrated over all causal paths from below by G at gamma of t times the causal speed. And then you can show that actually there is always a maximal weak subslope, and we call this norm of df. So we don't define what df is, we really define the whole thing here only. Then you get some calculus rules like concavity of the maximal weak subslope, you get locality, a chain rule. And then using that, actually, we can give a new proof of the smooth Lorentzian splitting theorem. Also, Nicola mentioned that, using the Q-D'Alembert version. instead of the Dallon version, because this is now an elliptic operator on time functions. And as Nicola mentioned, this avoids having to study all these space-like slices separately, but now you can give a direct proof using the Q-Dallon version. And this came out of this study of this non-smooth synthetic Lorentzian calculus of time functions. And this is the Lorentzian splitting theorem by Newman, Eschenburg, Galloway. So either M is globally hyperbolic or time-like geodesically complete. This means that every time-like geodesic, the maximal interval of definition is R, has non-negative Ricci curvature in time-like directions, then it contains a complete time-like line. Then it actually splits as a product, R times S, with this product metric, and S actually has also non-negative Ricci. There's a Riemannian manifold which has non-negative Ricci. Yeah. Yes. So and then so we gave a new proof which emphasizes that you gain ellipticity while losing linearity, and it is a more direct proof because you don't have to study these space-like slices, but also it allows you to start to give a proof of the splitting frame in low regularity. So if you're still in the space-time setting, but your metric is now of low regularity. So these tools also work then. And of course, the long-term goal would be to have a splitting frame for synthetic time like Ricci non-negative. Then another big question is, what is the natural notion of convergence in this Lorentzian setting? Because you don't have Gromov-Hausdorff convergence because you don't have a metric space. So what is the analog of Gromov-Hausdorff convergence here? We think we have something, but it's still not quite finished. And then there is another thing is that actually Alexandrov spaces with curvature bounded below, there you have coordinates and they're actually quite well behaved. Can you do something similar for Lorentzian length spaces which have time-like curvature bounded below in the triangle comparison sense? And also now there are several reformulations of these triangle comparison conditions, and one is the 4-point condition. And now you could even apply these time-like curvature bounds for discrete spaces, and that might have some applications to quantum gravity because these causal sets, they are discrete by nature, and there are even other approaches to quantum gravity where the fundamental paradigm is that space-time is actually not continuous, but on some fundamental scale, it's actually discrete. And these tools might help you to understand this better. Yeah, and then finally, let me take the opportunity and make some advertisements. So recently we got some funding. Yara, Raquel, Raquel, Mike, Roland, and myself, and also myself last year. So we might have a lot of positions and the call will open soon, but for now there is no website yet, but hopefully soon. So if you know some master students, recent PhDs or postdocs looking for positions to work in a field which is like on the intersection of metric geometry, optimal transport, Lorentzian geometry, and general relativity, just contact me or one of the other PIs. And it will start actually this summer, or this big project will start in October. Thank you very much.